in the field of chemical engineering, particularly polymer physics. And I met Daniel last year, and it was a very short, but indeed a very fruitful discussion. And I thought that it would be nice if we can invite Daniel to share his expertise regarding rheology, particularly for the biopolymer solutions. So, Daniel, time is yours.
Yeah, thank you so much. Yes, a very kind introduction. So welcome everybody, and thank you all for the invitation and for being here actually. And hopefully in the future we can also meet in person. So I usually start my presentation with the academy building, which is let's say the principal building of our university, located in the center of Groningen. So that's basically where all the fancy stuff occurs, including PhD defenses. So and I'm usually very proud of this picture because, as I said before, it's one of the fewest day in the Netherlands where you could see a blue sky, because most of the time is just gray and rainy. Yeah. Just to give you a little bit of information about like my background. So I started my studies in Italy, so especially in Sicily, and my bachelor was in nuclear engineering. So back then I was dealing with cold fusion and materials for cold fusion reactors. So my thesis actually was in a project of determining the viscoelastic properties of some sand used in cold fusion reactors in a sort of multinational project called eithin. So eventually I fell in love with these viscoelastic properties, and then I decided to move to chemical engineering for my master degree studies. And because it was back then the only course or the only program where you could study polymers. After that, I had a thesis at this multinational company, Italian one, this ENI. And I worked in this company right after my degree for almost 1 year. And I was doing a research on rubbers for the car tire industry. So I got bored of the industry life, like it was very static environment for me. And then in 2015, I decided to join a European so-called Marie Curie network. And I moved to Greece for my doctoral studies. So let's say the topic was mainly polymer physics and rheology, especially in colloidal systems, but eventually explored many more polymeric systems. So right after I got my PhD degree in 2019, I moved to Princeton for my first postdoctoral, let's say, research contract. And I was working on nanoflash precipitation, so how to make colloids out of solvent exchange phenomena. And then I moved to Penn State for one more postdoctoral research contract. And in there, I worked on flow-induced crystallization and rheology of biopolymers, which is actually just the beginning of my current research line. So in 2021, I decided to move back to Europe, and basically I became assistant professor in what I called rheology of complex polymeric systems. So, and basically here I am. And of course, so nothing could happen if it's not about group and teamwork. So I'm very proud to state that I have a very international and healthy, let's say, group with many students around, very motivated, very talented. And so this is a picture of a dinner we had together. So one dinner, 6 different nationalities. It's just fantastic. And this is actually what makes me proud of what I do and the environment slowly I'm building up. So this presentation is going to be about biopolymer solutions, but Actually, that's not the only thing that is going on in my let's say subgroup. We have also studies on complex conservation, 3D printable bioinks design, charged polymeric systems, gels for biomedical applications, and this is just, for instance, systems disperse or dissolved in media. But there is also another branch which is more into polymer melts, so compatibilization of polymer blends or designing biopolymer composites for body implants. So that's also something that is going on in my group. So the outline of this presentation is quite brief and simple. So I will just introduce the word of the natural polysaccharides and why I personally think that we should boost the knowledge of these materials. So just to have everybody on the same page, I will, let's say, deliver some basic concepts on shear rheology. And then I will show you two, let's say, directions of results we have obtained so far. One is the water-driven gelation of cellulose, native cellulose in ionic liquids. And another one is the phase diagram of agar in a composition-controlled binary solvent. So, and eventually ending up with some conclusions and take-home messages. So, many people over the years are saying, we should move to more sustainable materials. So we are driven by the fact that fossil fuel are diminishing, and also the processing of the same is not very easy and very energy consumption, and of course, nothing good for our environment. Nevertheless, I think that we are very far from replacing synthetic polymers, but we have very good reasons in order to study polysaccharides, biopolymers in general, and here I listed just three, let's say, reasons why we should take care of this. So first of all, sustainability and biodegradability. So something that many synthetic polymers, unfortunately, they cannot provide. Ecological safety, so we need to really reduce the impact on our environment. Industrial relevance. Now there is a big deal in the food industry. For instance, I have projects where the companies producing candies and cookies, they would like to use the plant-based biopolymers to replace synthetic or animally sourced biopolymers, for instance. So that's also there. Not to mention that biopolymers are now widely used in biomedical applications. So that's also something that we explore as well in my group. And yeah, so it is highly possible to produce functional materials, or let's say materials with some desired thermal or mechanical or optical properties. So these are very abundant, let's say, systems on Earth, because consider that native cellulose is the most abundant polymer on Earth, followed by chitosan, for instance, so coming from seashells or fungi. But the problem is that these materials are very complex. So, and for me, complex means that when we try to investigate their properties or their viscoelastic properties, the results do not conform with what we know from the standard or classic polymer physics framework. So we need to investigate their behavior much deeper. So we need to delve deeper into their properties. And just for today's presentation, I chose to show you a little bit of rheology of two systems. So one is on the left. So is this native cellulose, basically coming from wood, from plants mainly, and then a little bit of agar. So that basically forms very complicated structures when we try to dissolve it or disperse it. But what we can already say is that the two polymers, so they are not melt processable, so they need to be dissolved in something in let's say a very low viscosity medium. So the transition to special uses, of course, needs more understanding, and something that is very different from standard synthetic polymers. So their behavior changes completely depending on the solvent that we are using. So let me just say that native cellulose does not dissolve in water because of the strong hydrogen bonds that are basically occurring between cellulose or neighboring cellulose chains. But usually ionic liquids, imidazolum-based ionic liquids are able to dissolve cellulose, I would say, at the molecular level. Whereas agar, if you want, it has a very different hydrophilicity or hydrophobicity, because agar can in fact be dispersed in water, and it can form gels in water. But when it is dissolved in an ionic liquid, basically the same ionic liquids, so it forms what we call in polymer physics associating polymers. So the systems that I'm going to show you, they are both dissolved in this ethyl-methyl imidazolium acetate, which is a sort of standard non-toxic ionic liquid for cellulose and many actually natural polysaccharides. And the binary solvent would be constituted of ionic liquid and water. But before going into the results, let me just give you a little bit of background on what is small amplitude oscillatory shear, or let's say shear rheology in general. So the system is very simple. So you have a rheometer that can be schematized as shown here in this figure, where you have like a motor that provides a rotational deformation, and then an immobile top plate here that is connected to a transducer. So the sample is here squeezed between these two plates. So basically we are providing a shear deformation to the material. So the shear deformation can be provided into two ways. So either the motor provides a steady, let's say, a rotation with a constant speed that, of course, can vary, or you can have an oscillatory, let's say, deformation, where you have a certain, let's say, amplitude and a certain frequency. Okay, so usually this setup here is called the strain controlled rheometer, because as a matter of fact, the rheometer can control the strain, which is typically indicated with this Greek letter gamma. And basically we have the strain amplitude, so the amplitude of the deformation that we apply, times a sinusoidal, let's say, function, which depends on a certain frequency. Okay, so usually we want to probe our viscoelastic properties in conditions where this amplitude is very small, so that there is no disruptive, let's say, deformation to the material. And we call this linear viscoelastic regime. So if we just take the time derivative of this, we obtain the shear rate. So how much strain units we change as a function of time. And that's basically the cosinus of this input signal. Okay, so if this represents the input of our rheometer to our sample, so we are gonna get via the transducer resulting sinusoidal function, which is basically the stress. So we insert the strain via the rheometer, and we get the stress as a response. So you see that now the response has a sort of phase shift, which is this delta. And this is basically the nature of the viscoelasticity in polymers, because if I have this input and then I get the stress as a sigma as an output, I know that if this shift is equal to 0, so input and output are in phase. So we are measuring ideally elastic solid. If this delta is 90 degrees or pi half, okay, so it means that I input a sinus and I get a cosinus as a response, then it's a pure viscous liquid, like water, for instance. But if this delta is between 0 and 90 degrees, I have a viscoelastic fluid. Of course, if this delta is closer to 0, the elastic contribution is higher, and vice versa. If this delta is closer to 90 degrees, the material is more viscous. Okay, so the rheometer inside, well, via software, does this very simple calculation. It takes the stress, so it develops the sum of the sinus, and therefore we have in the stress two contributions. So one, which is the amplitude multiplied by the product between cosinus and sinus. This dependent on the delta or the phase shift, and this is frequency. And then another term, which is sinus of delta, cosinus of omega. So this term here and this term here can be basically called the elastic contribution, or G prime, and the loss or viscous contribution, also known as G double prime. So it goes without saying that if G prime is higher than G double prime, so the elastic contribution overcomes the viscous one. So the material is behaving like a viscoelastic solid. And the other way around, if G double prime is higher than G prime, so the viscous contribution is dominating over the elastic contribution. So this is just a way that the rheometer uses in order to understand whether a material is a viscoelastic liquid or a viscoelastic solid. Conveniently, there is another thing that we can get from the rheometer. I'm sure that you have heard about flow curves, or if you want, how the viscosity changes as a function of the deformation rate of a system. So most of the polymers are so-called shear thinning. So it means that for very low deformation rate, so the viscosity doesn't change. So you have a sort of Newtonian behavior. But then if you start increasing the deformation rate, the viscosity decreases, and this is known as a shear thinning behavior. And this is actually the reason why we are able to process, let's say, polymers, especially polymer melts, because the more you deform, the lower the viscosity becomes. So in this plot here, we are having not only the viscosity that we get from linear viscoelasticity, which is basically connected to G prime and G double prime, and we call this complex viscosity. But we can also use the rheometer in steady shear, let's say, deformation, where we can get the so-called steady shear viscosity. So there is a third way to get the viscosity, but okay, it's not really relevant over here. So with this, after this very brief introduction, let me show you the juice and the core of this presentation. So this is a cellulose, a native cellulose, basically from wood pulp, so which is basically dissolved in an ionic liquid at 2% in weight, and inside this syringe is basically a viscoelastic liquid. So when we just press the syringe, you can see that we are able to form a stripe of viscoelastic liquid that if you let it relax, it will basically flow. And this is just an empty Petri dish. But if at some point you brutally pour water on top of this fiber, okay, so that initially was a viscoelastic liquid, what we get in the end is a sort of hydrogel filament. So basically, we are able to obtain a hydrogel via solvent exchange. So water kicks in, So the ionic liquid is expelled, and then you can make nice fibers out of it. Another way to look at this phenomenon is actually to do the other way around. You have a bath with water, and then you have a syringe with the ionic liquid solution and cellulose, and then you can make really beautiful filaments underwater. Okay, that eventually you can measure the elongational, let's say, rheology or viscoelastic properties as well. So depending on the polymer concentration that you use, or for instance, how much water you take out, for instance, via heating, you can obtain very different fibers, or let's say fibers with very different properties. So basically, we can use these cellulose ionic liquid solutions to either devise injectable, let's say, materials, or even, let's say, 3D printing scaffolds for biomedical applications. So the physics behind this phenomenon is quite, let's say, simple. Although, of course, it took many years to understand it fully, or at least we believe we understood it fully. So imagine that we have here in blue the native cellulose chains, and this in green and red are the ionic liquid molecules constituted by a cation, imidazolium base, and the anion, the acetate. So as soon as you insert water molecules inside, so what happens is that the ionic liquid molecules will stop interacting with the polymer chains because they prefer to interact with water. So water and ionic liquid are 100% miscible. But as soon as you remove ionic liquid molecules from between neighboring cellulose chains, they start getting together again via hydrogen bonds, or as you prefer, is schematized here. So there are hydroxyl groups that basically favor hydrogen bonds, because the ionic liquid molecules, they prefer to interact with water molecules. So as a matter of fact, as soon as you insert the water, so you generate a sort of pseudo or effective crosslinks in the system, therefore promoting the formation of a gel. So we look at this phenomenon via photocorrelation imaging or photocorrelation spectroscopy. So basically, it's a sort of dynamic light scattering technique where you can have information about correlation functions or decaying correlation functions in terms of time, but also in terms of position. So the experiment was quite simple. We had a capillary. We inserted cellulose solutions, which is a viscoelastic liquid in dry conditions. And then we started adding, let's say, a water reservoir on top of this, let's say, cellulose solutions. And then we were monitoring how the water diffuses inside the solution. So here, everything is dark, and this is basically at time equal to 0. So there was no water. Then we insert water, and then you start seeing all this multispeckle popping up. So, and this is basically the interactions of water with the solution. And this is basically how the gelation front moves inside the sample. So if you want, this is the part where the solution is in contact with water. And this is basically the bottom of the capillary. So after 13 hours, almost the whole solution becomes a gel. So this means that if we just collect the autocorrelation functions as a function of Z, so the depth of the capillary, and as a function of time, we get all this correlation length, all these autocorrelation decay functions. So we can get the time at which each correlation decay exhibits, and plot it in this way. So we have Z squares, so which is a sort of mean square displacement as a function of time. And what we observe is that this square of the size as a function of time scales linearly. So it means that the process or the gelation process is a diffusive process, so something that was not very granted from the beginning. So it looks like that this gelation fronts evolves linearly, it's diffusive, and it moves like a sort of plug flow, as you can see from this video here. So this is just a sped up video because it took us 16 hours to just record it. But if you can see, let me show you again, perhaps. So the gelation front moves really like a sort of plug flow. Yeah, so it's quite homogeneous with a very, let's say, linear function from the position and time. So it's a diffusive way of gelation. So we could look at the same thing rheologically. So we start from a dry solution. So we have a liquid. So we are seeing in this plot G prime, which is the elastic contribution to the total response, and G double prime, which is the viscous contribution to the total response. And here in the x-axis, we have the oscillation frequency. So at high frequency, G prime is larger than G double prime, so it's a viscoelastic solid. But then at very low frequency, or if you want at large relaxation times, the inverse of the frequency, so the material becomes a liquid. Okay. As soon as we start adding a little bit of water, so you see that for the all frequency range explored, G prime is always higher than G double prime. So we got what we called an arrested state, or the system gets dynamically arrested. So something that we noticed is the fact that there are sort of two plateaus in G prime that we can notice. One is here in the high frequency, so and one is basically here in the low frequency. So this one, which is very close to the dry state, is basically the elastic modulus related to the entanglements. Or if you want to, you can imagine the network of polymer chains like this, where the entanglements in physics are basically these physical constraints between chains from the theory of Dejean and Edwards. Therefore, the plateau modulus or the elasticity is dictated by how tight this network is, or if you want, the molecular weight between two consecutive entanglements. On the other hand, this low frequency elastic modulus is dictated by the crosslinks that we are forming because of the water addition. So this means that we are going to have a sort of effective double networks. So the first network is exerted by the entanglements, and the second network is basically dictated by the consecutive crosslinks. Okay, and if you prefer to see it this way, so water acts as a sort of crosslink density. The more water you add, the more crosslinks you form, and the tighter the network becomes. And in fact, as soon as you add the more and more water, the gel becomes much stronger. So basically, just by increasing the amount of water of 1 order of magnitude, so the modulus here increases by 2 orders of magnitude. So from 100 Pascal to 10,000 Pascal. So if you want to, you can regulate the elasticity of the system in a sort of elegant way just by adding water, which is a sort of counterintuitive for many of the jelly systems. So we can have a sort of diagram where we plot here the elastic plateau modulus as a function of water concentration. And we could see these plots as a sort of phase diagram, if you want, because different colors relate to different polymer concentration or initial polymer concentration. So empty symbols mean that the solutions are liquid, whereas let's say half-filled let's say, symbols are materials that became gels. But in this case, there are two, let's say, plateau moduli. One is dictated by the entanglements, and another one is dictated by the crosslinks. And then eventually for very high content of water, so there are much more crosslinks and many more than entanglements. So that basically the network is dictated by the number of crosslinks rather than the number of entanglements. And you see that there is a huge power law relation between the modulus and water concentration. So we applied some polymer physics here. So usually we know that if we divide the modulus by the polymer concentration to the power of 2, this function should basically scale and put all the data together into a sort of a master curve with the crosslink density. It's just that here, instead of the crosslink density, we have water concentration, but effectively it's like an effective crosslink density. So you see that when we apply this ploy, so all the data collapse together. So we were able to detect or to determine a sort of scaling law that is very powerful in terms of materials design, because you can basically choose the modulus that you want the gel to have, and then you just select the polymer concentration and the water content that you need to have. So if you know 2 of them, you get automatically the third one from this equation. Or if you start from a polymer concentration and you start adding a certain amount of water, you can already predict what the modulus could be. So, and usually modulus means elasticity, and elasticity means processing. So if we take synthetic physically crosslink networks, so usually it scales with the crosslink density to the power of 1. So whereas our system is with the crosslink density or effective crosslink density to the power of 3. So it's a much stronger dependence compared to, let's say, synthetic polymers. And this has to do most probably with the fact that natural polymers are much more rigid than synthetic polymer chains, or because during the formation of gels, higher order structures are formed, so like for instance bundles or clusters or even helices, for instance. So a recent work published in Macromolecules, so they also find with polyacrylonitrile polymer in DMSO and water a power of 1.6. And usually this polymer is a little bit more rigid than other synthetic polymers that we have witnessed in the literature. So the effect of water can also be, let's say, investigated by a Raman spectroscopy. So basically, we wanted to ask ourselves the question, so when I insert a lot of water in the system, for instance, 100% of water, so do I still have ionic liquid in there, or the ionic liquid is completely expelled from the system? So this brought us to, let's say, more atomistic experiments. So we measure the first the MEMAC, so just the ionic liquid, which is in brown here, and then a dry solution, so in green. And basically we figure that most of the Raman signal comes from the ionic liquid and not from the cellulose itself. So it's a sort of indirect contrast that we have. We basically check what happens to the solvent when we add water in the presence of cellulose, rather than looking at the cellulose when we add water. So what we witnessed is that this peak here, which basically relates to the vibration of this group here, so it's basically the carbon-oxygen group of our ionic liquid. So, and then what happens is that as soon as you increase the water amount, this peak becomes weaker and also shift towards larger Raman shifts, or if you want to do, let's say, a larger, or let's say a smaller length scales. This is because at some point the acetate will start interacting with water, as it is also shown in this cartoon here. And water is a much smaller molecule compared to the cation. So this is basically what we are seeing here. Eventually, when we have 100% of water, so there is no signal anymore. So it's basically the same as the background, meaning that we are not able to detect ionic liquid anymore. So we cannot say that it's not there absolutely, but certainly not in an amount that is detectable experimentally. So this is how, for instance, a stripe of ionic liquid looks when it's completely like dipped into water. This is basically the instantaneous effect we have. And this is basically how this sort of hydrogel becomes after 24 hours. You see that it becomes a very turbid, very opaque, hinting at the formation of very large clusters, or at least of the order of microns. So there was a question here, are we forming any crystalline domains? So for this reason, we run some wide angle X-rays, and everything looked pretty much isotropic. So we couldn't, let's say, detect any Bragg peaks. So it really looks like either microphase separations or the formation of very big clusters among cellulose chains. So what we can see from here is just something that is similar to what we witnessed with the Raman spectroscopy, that as soon as you add water, so this peak here shifts towards larger, let's say, scattering wave vectors or smaller length scales, again suggesting that we are replacing the cation with a much smaller molecules, which is basically water molecules. Some cryo-TM experiments, they also show that in dry conditions, everything is very homogeneous. We could not see anything, but in wet stage, you start seeing a very, let's say, big spot, most probably hinting at some big clusters of cellulose and water. We have performed some nonlinear shear experiments as well. So meaning that now we provide the strong flows or strong deformations to the materials. So these plots, they may look very busy, but I'm going to break them down for you. So here we have the complex viscosity. So depicted as, let's say, open symbols here. Different colors is basically different amount of water, if you want. And the closed symbols is the viscosity measured, let's say, during a strong steady shear condition. So you see that when there is no water, so dry conditions, the two viscosities are basically the same. But as soon as you form the gel, so the steady shear viscosity is always smaller than the complex viscosity or the viscosity measured in the linear viscoelastic regime, meaning that the strong shear flow is basically destroying all these sort of bundles or clusters that forms during the gelation process. And it seems that the more water you add into the system, the larger the difference becomes between complex viscosity and steady shear viscosity. When we plot the stress as a function of the shear deformation for the dry solution, everything follows, let's say, what we expect from polymer physics. So in the linear regime, stress and deformation are linearly dependent. And then at some point, when the nonlinear regime is attained, we have a much weaker dependence of the stress on the deformation rate. But for the gels, something very strange happens. So that basically the stress doesn't really change with the deformation rate. It seems to be constant. And this is a very known flow instability called shear bending. So meaning that there are different bands in the fluid, if you want, in the velocity gradients. So where there are layers of fluid moving faster, but with a lower viscosity, and other layers moving slower and with the high viscosity. So since that the stress is basically the product between the shear rate and the viscosity, so this product is basically constant. Okay, so and this has been seen actually with colloidal gels exhibiting, let's say, strong shear bending. So this brings me to, let's say, the second and last topic. So here we now have agar. So let me remind you that agar is partially soluble in water. And in fact, it can even make gels like in water. So let's say it's more hydrophilic than cellulose. And here we are reporting the viscosity as a function of water content. So it means that when the content of water tends to 0, so that's log-log plots, so there is no 0 here, is basically the pure ionic liquid used as a solvent. So in here we obtain the so-called viscoelastic liquid. Interestingly, as soon as you start adding water, the viscosity drops. So meaning that the cellulose chains are still, the agar chains are still far apart, as I sketched over here. And the water is just interacting with the ionic liquid. And if you want, it's just lowering down the viscosity of the dissolving medium, because the water has a much lower viscosity compared to the ionic liquids. So, but as soon as the agar chains are able to interact with water as well, they start forming this double helices. Okay, so and the viscosity starts increasing again. Okay, until a certain point, so the viscoelastic liquid is replaced by a weak viscoelastic solid here. However, when we shift the content of water between 30 and 40%, there is a huge, let's say, shift in viscosity. We are talking about 2 orders of magnitudes of difference in viscosity, because all these double helices start forming, let's say, cross-linking point. So they basically form a network. And as you can see from this rheology plot, so the storage modulus is always much higher than the viscous modulus, suggesting a strong, let's say, viscoelastic solid, namely a gel. So the condition here that the initial polymer concentration must be higher than the entanglement concentration. So meaning that's in dry conditions, so the agarose chains should form entanglements. So in polymers, and especially I would say polymer physics, is very important to know scaling laws, because scaling laws are pivotal for designing, let's say, tools and devising materials with desired properties. So we need to know that we already know from polymer physics that the elastic modulus as a function of polymer concentration usually scales with the power of 2.3. So this is both for, let's say, theta solvent or good solvency conditions. But when we form gels, so in, for instance, in water or just by adding water, so this power law increases to 3. We have observed with many natural polysaccharides that this is a sort of common finding. So every time we plot the modulus as a function of polymer concentration, so the power law is much stronger compared to, let's say, synthetic polymer chains or polymer chains without the presence of water. So this means that if we plot the relaxation time of the material, so the terminal relaxation time, so or if you want the time scale at which typical polymer chain diffuses fully from its own network. And this is basically the scaling laws we know for good solvency condition and theta conditions. But then you see that for our systems, we have a much stronger, let's say, power law. So this means that when we plot the viscosity and we witness this very strong dependence, so we are talking about associating, let's say, polymers. Just as a sort of reminder, non-associating polymers, they would exhibit a 4.7, let's say, a slope with concentration. So it was in 2022, yes, that's we developed a sort of molecular model that we call the sticky blob model to describe the basically the dependence of the viscosity on polymer concentration for strongly associating polymers. Back then, it was for polyvinyl alcohol, let's say, solutions, but this equally applies to biopolymers or biopolymer solutions as well. So something can also be drawn for anisotropy under strong deformation. So this is just a very, let's say, deep rheological functions that to some extent gives you the anisotropy of the system when it's sheared severely. For instance, the processing, this is how the degree of anisotropy depends on the deformation rate. And this is basically something similar that we obtain for water and for ionic liquids. So until you basically reach a certain degree of stretching of the chains, nothing happens. But when all the polymer chains are stretched, this anisotropy increases with the power of 0.2. And this has been seen also with many synthetic polymers as well. So to conclude this presentation, I would like just to highlight these points here. So we had two plant-based biopolymers having the different degree of hydrophobicity, cellulose and agar. So they exhibit a very different sol-gel transition and dynamics when water is added to the system. And we can use water, or if you want ionic liquid, depending the point you start from, to tailor viscoelasticity. And especially in native cellulose gels, the strength of it can be, let's say, regulated in a very elegant way with the water content, acting as a cross-linking density. And we came up with some scaling laws so that they are really beyond any traditional cross-link network and allows us to design gels for 3D printers, for instance, so bioinks, or to devise, let's say, gels in general for applications. So agar and ionic liquid solutions. So we have this unprecedented reported non-monotonic behavior of the viscosity with increasing water. So there is a minimum there. And in general, the message is that plant-based biopolymers offer a large tunability and rheological properties just by playing with solvent. And we are just scratching the surface, I would say, because there is really a lot of stuff to know about these polymers. Of course, I need to acknowledge Roshan and Wenji, who are sitting here next to me. That's basically run most of the experiments in this work, and basically various collaborators from cryo-TM, photocorrelation imaging in France, and of course, a very close collaborator of mine, Professor Colby at Penn State. And of course, all of you for your attention. I'll be happy to get any question, comments, or remarks.
Yeah, thank you very much, Daniel. Yeah, very nice presentations. With this, I invite questions from the floor. Yeah, please, question, please. Yeah. Okay.
Feel free to ask any question, and I hope it was a little bit clear with the some basic concept that I provided.
Yeah, thank you, Daniel. Yeah, well, to start, as you mentioned that the modulus elasticity, according to your experiments, you found that the modulus elasticity is very much depend on the polymer concentrations with the power of 2, if I'm not mistaken. Yeah?
Yeah, exactly.
Yeah.
Yeah.
Does it applies for all biopolymer, or it is only in your case on your selected
So
biopolymer?
this is very universal. So because this scaling law
Okay.
actually comes from synthetic polymers. So because synthetic polymers are those that we know the most, let's say. So we said, okay, let's see if the scaling for polymer concentration works well if we adopt that for synthetic polymers. So it seems that the polymer concentration is something that's yeah, it's something universal. So it
Okay.
works pretty well with native cellulose as well. At least, yeah, that was our feeling. Yeah, only the water content is very different from what we know in terms of crosslink density, but it is also true that so we say that water acts as a cross-linker, but it's of course much more than that. It's a much more different physics, I would say.
Okay, so this is a universal equations, yeah?
Yeah, so this is a sort of a valid equation. It just that the power law here for the water content seems to be strongly dependent on the rigidity of the polymer chain.
The polymers, yeah. Okay.
Yeah.
Yeah.
But it's a quite
mm-hmm.
interesting tool because you see, like you change a little bit the water content, but then you have a log scale here. You can change the modulus almost at wish. So it's very sensitive to water.
Yeah. Okay. Thank you, Daniel. Is there any questions from the participants?
So
Okay,
too shy to.
yeah, perhaps. Yeah. Daniel, is there any rule of thumb on the selections of the ionic liquid that we can work with the biopolymer?
Sorry, can you say it again?
Is there any rule of thumb, or how do we know the miscibility
Yeah.
of our biopolymer or with the several types of ionic liquid?
Oh, this is an excellent question. It's there are not so many ionic liquids that can be used. I think we can even count with one hand, so 4, 5. And in my group, we are mainly using like a 3, and they are all imidazolium-based, let's say, ionic liquids. So my understanding is that basically the size of the cation plays a huge role in dissolving polysaccharides. So basically, it seems that the cation, imidazolium-based, sits perfectly between, for instance, the non-polar groups of cellulose chains. So therefore, it is able to really form a layer around the single cellulose chain, for instance, preventing it from connecting via hydrogen bonds to a neighboring chains. So it has to do with interactions, but also with the static hindrance of the cation. So if, for instance, you take another ionic liquid, which is not imidazolium-based, it does not dissolve. So, and this is actually the whole challenge, because many people try to use deep eutectic solvents to dissolve polysaccharides, just because deep eutectic solvents can be much greener. But as a matter of fact, none of them dissolve cellulose at the molecular level. Not to mention that if you have another polysaccharide, like for instance, potato starch, so where you also have branched, let's say, parts of polymer, then it's even, let's say, more difficult to dissolve it in a solvent. So I think for some polysaccharides, especially the branch ones, not even the imidazolum-based ionic liquid can do the job. But nevertheless, if we want to understand biopolymers, so that's the way to go. We first need to understand how they behave in a good solvent.
Exactly. Yeah.
Yeah.
Yeah. So, fantastic. And Daniel, most of the participants here are our undergraduate students, yeah, which I believe that none of them has experience on evaluating the output of the rheology measurement. And
Yeah.
then can you give brief introductions regarding how do they interpret the stress as a functions of the shear deformation. If I'm not mistaken, you provide this curve on your slides for 26 or 27, yeah? When I was slides 26 or 27,
Yeah,
this
this
one.
one.
Yeah. Yeah, and then as you said that there is a linear region and also non-linear region. Can you tell them
Okay.
what is the importance of knowing the linear and non-linear region?
Sure.
Yeah.
Again, fantastic question, and I'm very glad that you asked, because as a matter of fact, these are a little bit more advanced, let's say, plots, but I decided to include them because I think it's something very standing out from these gels. So first of all, when we talk about linear regime, and I mentioned this many times, we need to understand what is linear with what. So it's that basically it comes from the Hooke's law. That's the stress linearly depends on the deformation. So it means that if I double the stress, the deformation doubles as well. So that's basically the main concept. So this behavior is true only when you apply very small deformation to a material. So a small deformation, meaning that you do not disrupt, for instance, the network of a polymeric system. Okay. However, when you start increasing the deformation, or if you want the deformation rate, so how much you deform the system as a function of time, if you want, or as a function of, I don't know, rotation per minute in a rotational rheometer. So anyway, something that contains the time. So when this deformation becomes very severe or very large, then you start breaking the structure of the polymeric network. So meaning that this is what happens, for instance, when you have a polymer solution that is injected via a needle, or when you have a gel in a 3D printer. So you are providing a very strong flow. So you can expect to deform and to disrupt the polymeric network. So it is important to mimic this behavior, because when you want to process a gel, you need to know how the system behaves when you deform it. So this is just to give an idea. So it means that we can have rheologically two types of viscosity. One viscosity that we call it eta star here is the viscosity that we detect, let's say, when almost no deformation is provided to the material. Okay, and then we have this other viscosity with no star, which is the viscosity that we attain during steady shear, let's say, deformation of the material. It's like I have my rheometer, the sample is sandwiched between two plates, and basically one plate rotates continuously. Okay, so when the viscosity of this strong flow is much lower than the one that you measure, let's say, under strong deformation, it means that the flow and the strong flow you are providing to the material is basically disrupting the network significantly. So whatever is formed there in terms of, for instance, bundles or double helices, so everything is basically disrupted by the flow. So this means that you know what is the viscosity at rest, but you also know what could be the viscosity during processing, for instance, during a 3D printing. So for instance, typically a 3D printer provides a deformation rate of about 100 reciprocal seconds, okay? So 100 strain units in 1 second. So this is the typical deformation rate during printing. So it means that when I have this gel, let's look at the blue, for instance, as a reference, I know that the viscosity is already 1 order of magnitude, more than 1 order of magnitude lower compared to the viscosity of the material, if you want, at rest. So did I give more or less the idea of why this is important and why we care about the, let's say, non-linear viscosity? Because the same thing can be witnessed basically if we look at the stress. So this is basically the shear stress provided to the system, and this is the deformation rate, okay? So it means that when the system is a liquid, so you see that there is a slope of 1. So if the deformation rate is basically below 5 or something like this, so everything is basically the sample is not feeling such a strong deformation. But then at some point when this nonlinear regime is attained, so the slope becomes 0.3, which is something that we know from theory. So this is for a very simple systems. However, when you have gels, you know that the viscosity is indeed decreasing, but the stress that the material basically exert is just constant. And this has to do with the fact that there are a lot of instabilities of flow in these complicated systems. So this, for instance, in terms of printing design is also very important, because stress means, if you want, the pressure that you need to apply to the 3D printer to let the gel coming out from the die, right? So how strong you need to push if you want the system to get it out?
Yeah, indeed, it is a very complex one, Daniel.
Yeah. Absolutely.
And
It just to show you that all this information is just to connect molecular structure to processing, and rheology is in the middle.
yeah, and also interestingly that you can tailor your let's say your products based on these fundamental aspects. Yeah, you can play around with several biopolymer solutions. Yeah, based on their rheological behavior.
Yeah, absolutely. And I didn't present it here, but we have a very wide collection of results of biopolymers. Because we measured really many polysaccharides, carrageenan, chitosan. So it just that I didn't really want to bombard you with all this data, but we have really quite some knowledge on nature of polysaccharides. So yeah, we always like to do fundamental studies, and especially connecting the molecular structure to processing. So that's basically our aim, and how we should use certain polysaccharides for certain applications. So to basically provide the guidelines for materials design.
I do agree with you. Please don't gun shoot us at this very short time being, Daniel.
Yeah, absolutely. I also wanted to say, please go ahead.
Yeah, go ahead, Daniel.
No, I just want to say that I can share this presentation with you. Maybe you can also share it internally in case someone would like to look at it more into details, and maybe want to ask me questions via email. Like I usually provide the the presentation for instance, let's say a posteriori feedback or questions.
Yeah, would be nice then. Yeah. Probably afterwards there will be communications among participants and you. Yeah. You, if I'm not mistaken, you already put your email address right on your slide.
Yeah, it's my email address in the last slide. Yeah. So everybody can contact me. Yeah. So
yeah.
it's
Okay.
basically.
So. Yeah. Daniel, I don't want to reserve you for a longer time. Yeah, I know it's many things to do. Yeah. So on behalf of physics department, yeah, I would like to say thank you for your kindness sharing on very fundamental aspects, and it's very interesting, particularly Indonesia. We have a biodiversity and also, of course, the diversity in biopolymers. Yeah. And of course, we are looking forward to your future lectures, yeah, regarding our summer course. Yeah, hopefully we can manage to invite you in person to Bogor. Yeah, so dear students, yeah, we are planning to invite Daniel to Indonesia in this June. Yeah, so please wish us luck, yeah, to be able to fly Daniel to IPB, yeah. Okay, Daniel, as a
it would be
token of
a
appreciation,
honor to be there. Yeah,
would be nice then. As a token of appreciation, so we have electronic certificate here. Then probably the secretariat will share it to you. It's a kind of
thank you.
just for remembering that you have shared very interesting talks to us.
That's very kind.
Yeah.
That's very nice. Thank you so much.
Yeah. Okay. Thank you so much,
Okay.
Daniel.
Thank you again, and
or
yeah,
you want
we
to
keep
say
in
something?
touch.
Yeah.
No, we stay in touch.
Perfect.
Yeah. Bye everybody.
Okay. Yeah, we'll be.
Bye.
Yeah, thank you. Bye. Yeah.
Thank
you for all
you.
participants
Thank
as well
you,
as
Daniel.
Pak Tony.
Yeah,
Yeah,
thank you,
and others.
Daniel.
Yeah.
Bye.
Yeah. Bye bye.